Good morning, everyone. I don't know if you can hear me.
Good morning, Artur.
Good morning. Well, I would like to thank you all for being present today on the FODIAC webinar. On behalf of Lorenzo, I want to apologize. He will join us during the meeting. Today we'll have two talks. Cristina Prieto from Bioinicia will talk a little bit about electrospinning techniques. And afterwards, we'll have Ricardo Pereira from the University of Minho, and he will talk a little bit about home heating technology. I don't know if we can start already. Cristina, are you able to start?
Yes, we are able, but we are going to share the presentation between my colleague Maria Pardo, that is responsible of the electrospinning and fibers production, and then I will present the electrospraying technology.
Okay, perfect.
Hello.
Hi, Maria. Good morning.
Good morning. So shall I share the screen now? Hello?
Hello, Maria.
Can I share the screen now? I don't know why
Sure.
people keep coming and going. I don't know what's going on. Okay. Can you all see it then? Very good.
Yes, we can see.
Very good. So hello, everyone. My name is Maria Pardo. I work at the R&D department at Bioinicia. And as my colleague Cristina said, we are gonna do this presentation together, and we are gonna talk about the technology of electrohydrodynamic processing. Just to give you an overview about how the presentation is gonna go, I will start presenting a little bit of introduction on electrospinning and the case studies that we have at Bioinicia. Because it's my main field of expertise, whilst Cristina Prieto is more focused on the electrospraying technology, and so she will then introduce us to this technology, and we'll talk about a few case studies, and also about our technology capsule tech. Just for the ones of you that you don't know, so Bioinicia is started off in 2009 as a spin-off of the Spanish Council for Scientific Research. We started off just giving a small product development processes and services for clients, and it escalated from there. And in 2012, we created our own FODIAC electrospraying equipment. And if you happen to pop up by our website, you will probably see that there is a wide range of equipment that we've managed to develop, from the very basic research with our FODIAC LE10 to a very high throughput industrial fabrication with a FODIAC LE500, which is all over the world already, because this technology has had a boost in scalability over the past years. So more and more people are using it in a more industrial level. So we went on from there, creating our own first in the world GMP certified plant for biomedical devices. And from there, now up to 2020, we are now on the production of our own brand Prevail face masks. So just to give you an overview of how many fields we touch at Bioinicia and CSIC as well, from pharma to biomedical to food to now filtration. Within the project of FODIAC, we've grown a lot over the years. but the main people involved in the project and who have done or will do the secondments are in these little pictures from here. You may know already Jorge Teno, Alberto Chiva, or even myself, who already did our secondments. And then we have Alvaro, Jose Luis, and Enma, who are in the R&D part, although Jose Luis is a little bit more in the project management part of it. But they will do their secondments if the pandemic allows it, of course. From the part of the CSIC, my colleague Cristina works there, and she may give you a bit of an overview about all the work they do over there later. But because Bioinicia was born within this research group led by Jose Maria Lagaron, we do very similar things regarding electrospinning and electrospraying, although at IATA CSIC they got a more strong focus on food packaging and food encapsulation, and it's all more at a lab scale. Both of us are based in Valencia, and if you happen to have a secondment here, it's always very sunny. Regarding our work in FODIAC, mainly the main driven that we had when we've done our secondments has been trying to use our technology, in this case electrospraying, to try and efficiently encapsulate bioactive extracts such as polyphenols or flavonoids in order to protect this and try and stabilize them and improve their viability. The main work we've done is try to optimize the electrospraying process, which is a challenging part when using certain materials or certain solutions, and go through the whole encapsulated and microparticle characterization. I'm sure some of you have worked in electrohydrodynamic processing, but just to give you an overview how this technology works. So basically, you have your polymeric solution that is placed in a syringe that is being pumped through a nozzle. And this, you can apply some electrical voltage and generate an electrical field within this nozzle. Then depending on the characteristics of your solution or even the parameters of the electrospraying or electrospinning process that you are applying, you may get either a finely dispersed powder into your collector, which will be electrospraying, or you will be making a continuous non-woven material that sometimes even looks like a normal paper, and then you will be making fibers, and this will be called electrospinning. It's a very versatile technology, mainly because, especially for encapsulation, because it's done at room temperature, which means you can be able to process and encapsulate thermolabile components. And you can do a lot of things with this technology because you can change the physical chemistry. Parameters of your solution will turn into a change on your process. The type of nozzle, the type of collector, all these things will contribute positively if you change them well, or negatively to your process. And so you can get a wide range of different morphologies, or even from the texture, you can get fluffy to very flat non-woven materials. And obviously you can make them from synthetic polymers, biopolymers, or you can even make nanocomposites for things like sensors. The same applies to the particles, but because we are mainly going to focus on electrospinning in this part, I'm just talking about the non-woven materials. So obviously, because you can use this technology and by changing different parameters, either in electrospinning or in your solution, you can fine-tune your material. This can be used in many different fields. However, for the sake of the time, we are gonna just talk about some case studies at Bioinicia regarding food packaging, cosmetics, and drug delivery, which are the main, the strong applications that we have at Bioinicia. Regarding food packaging, one of the main projects that we had at Bioinicia that we successfully achieved was to try and generate tubes like the one you see here, with a coating in the inside that was water repellent. So you could, for example, if you have your tube with water-based cream or your bottle of ketchup, when you are about to finish it, you would not have to worry about the wall being left with all the residual cream or food there. So with this coating, you could have the whole material going down, and you could, first of all, use it all. So we would save money, and the customer could be happier because the whole material, the whole product is being used up. And this would ease the recyclability of the tube because there won't be much material left there. And overall would reduce waste in both the packaging and the product that is inside it. We did this with a multi-step process where we apply a layer of electrospinning, a layer of electrospraying, and then we applied a thermal annealing pressure without pressure, sorry, in order to, this thermal treatment was just to try and stick together the two layers, because one of the main issues with these coatings is that they peel off quite easily. So this is the very first approach that we did, where we had two injectors and we were electrospinning and electrospraying at the same time. And after that, we moved it onto the picture on the right, where we built an entire equipment just for this, where the roll was going all the way from the table, where we did the sequential electrospinning, electrospraying, to a thermal lamp, and finally to a roll-to-roll collector. After we did this treatment, when we reached to the end of the roll-to-roll collector, one of the quickest ways to see whether it had worked, it was just to put a few droplets of water onto the material, which in this case, I think it was low density polyethylene. And we could see that they were clearly super hydrophobic. Obviously, because we need a lid for these tubes, we try and also to coat on non-planar substrates, in this case these lids, which was very tricky, but at the end we managed as well to coat it homogeneously, and we managed to get super hydrophobicity on these lids as well. As a proof of concept, we built these tubes, we put a water-based gel and also ketchup onto them, and we created a panel where we made people push it through to the end, like you would do when you are running out of your cream or your gel and you want to take it all out. And as you can see here, when you had a non-coated tube, there was always way more material in the walls that there was in the coated one, and this could we did this by weight differences, and there were significant differences on this, not just visually but also quantitatively. And we have not shown in here, but we also did some migration studies and indicated that there was no migration of the coating, especially for the particles onto this material. So that was very successful as well. Moving from the food packaging to the cosmetic area, at Bioinicia we have been able to mass produce different face masks for beauty masks. This has been, we have done it with just making the carrier, but also doing the whole mask and encapsulating the active ingredient. This field is, the electrospinning is very advantageous in this field mainly because current technologies now, current beauty masks are mainly based on wet masks, where people basically take the carrier and impregnate this carrier onto a solution of the active ingredient. The thing is with this, you need to preserve somehow the active ingredient which is floating around there. And people use preservatives and such. And plus, you've got to keep moisture the whole mask. With this technology, you can efficiently encapsulate the active ingredient there, which means you don't have to worry about adding preservatives on it, because it's somehow protected within the fiber. And also you've got your dry material, which is from the consumer point of view is more acceptable, is easier to handle at least. In this particular case that we are going to show here, Bioinicia took part of mass producing the carrier. And then there was another company who took care of impregnated the complex that we use, which was kitting lining complexes. So we did the white part of the mask, and then the other company took care of impregnating these complexes, as you can see in the small dots here. And with the SEM, you will see that the different complexes, the different small particles have been homogeneously distributed within the fibers that we made at Bioinicia. We did this, we ran a human panel study on this as well, just to see the effectiveness of the beauty mask that we had created. And we looked at the reduction of wrinkles. We looked as well at the hydration levels of the skin, firmness, and also elasticity. People were only using this mask once per week. Measurements were done after 15 days and 30 days. Just for the length of the wrinkles, if you look at this graph, we look at the green bars, which are the mask with the impregnated material, and the green bars are the ones with the placebo, just with the electrospun carrier. You can see the reduction on the length of the wrinkles is quite significant, from 0 to 15 days, and it maintains until 30 days. But if we look at the other parameters as well, there are even significant differences just by looking at the treatment with the placebo, which is with the electrospun carrier, which may indicate that even just the topography of the face of the placebo face mask itself, made with nanofibers, and perhaps as well the nature of the polymer that is made of, contributed as well. But overall, there was an increase in skin hydration, skin firmness, and even for the placebo, there was a significant, the elasticity was maintained. The beauty of this as well is after we finished this study, we gave a questionnaire to the volunteers about the perception. What did they think? Did they think that their skin looked better? Was the product good? Did it smell good, bad? Did it look good? And nicely, the quantitative data was matching with the qualitative data, in the sense that we observed that the wrinkles were reduced. Well, people could see that they looked younger in a way. From the commercial point of view, they also thought that the vast majority of the mask had a nice color, and the perfume was okay. So these are very good insights towards commercialization. Then moving on to the pharma products that we have also worked on at Bioinicia. This is one of the very strong lines that we have here, where we are trying to encapsulate active pharmaceutical ingredients, APIs, that are not very friendly when you try and have them orally. we are trying to put them into different patches, either transdermal, vaginal, mucosal, so we avoid that they go through the first pass effect. And we try, with this technology, try to increase their bioavailability as well. And we have had various cases of studies with antibiotics, such as ciprofloxacin, with Parkinson's disease treatment drugs like ropinirole, and in this case, for drugs for heart disease treatments, such as carvedilol. And we have seen at Bioinicia that just by using XYZ polymers and also their blends, we can modulate the release that we have. We can control it. So we have been able to make ad hoc patches to generate to deliver certain amounts of drug at the time that we prefer. Whether we want to have a patch for 1 hour or 6 hours, we can modulate this with the know-how that we now have. And in this particular case, for the carvedilol, for example, we have also observed that when we compare with the CF, which means with the cast films, we can see that the drug delivery, the solution of the drug is higher and is better for our fibers, which is good in cases for water, for poorly water-soluble drugs, as is the case of the carvedilol. So that was all for the case of electrospinning and for the case studies that we have for Bioinicia. Sorry if I went too fast. Now I give the floor to my colleague Cristina for talking about electrospraying.
Thank you, Maria. You need to stop sharing the screen.
Yeah.
Thanks. Okay, so let's continue with the electrospraying. And we are developing new products to address different aspects of the social life. And in the case of the FODIAC product, we are increasing the well-being of the elderly people. And we are creating those new products, functional foods, for example, that contain bioactive compounds. In this case, it's polyphenols and flavonoids, but there are a lot of bioactive compounds that could be included in these products. However, those bioactives are highly sensitive to different physicochemical parameters that provoke a loss in biological functionality and bioavailability. And an alternative that is the objective of the FODIAC project is to encapsulate those bioactives to maintain the biological functionality and bioavailability, provide its controlled release, and also mask undesirable organoleptic properties, avoid adverse effects, increase the shelf life, and also provide easier handling. There has been developed a lot of encapsulating methods, such as spray drying, freeze drying, coacervation, or supercritical fluid technology, being the spray drying the most used in the industry. However, this technology uses high temperature that could degrade the bioactive compounds. And for example, in the case of freeze drying, it generates irregular or highly porous structures that also could affect the stability. And in case of coacervation, they use organic solvents and toxic reactives that could affect the applicability of the particles in, for example, in a food product. And in the case of the high supercritical technology, it requires a high capital cost due to the safety measurements. When we are talking about electrospraying, this is a highly versatile technology because we can create particles in the nano or the micro scale, and also with different structures, since they can be single core or multi-core, just changing the needle or the configuration of the nozzle, or changing the solution. We can part from a solution or an emulsion. So it's a highly versatile technology. And we can also encapsulate different kinds of bioactives. being hydrophilic or hydrophobic, in this case polyphenols and flavonoids. And also they can be encapsulated in different types of materials. If we compare the technologies, for example, the spray drying, this technology uses high temperature, and the bioactive is homogeneously distributed in the particles, so they can also be on the surface. However, when we encapsulate through the electrospraying technology, we use voltage first to generate small droplets that can dry at room temperature, and also the use of the voltage allows the components of the solution to reorganize, and being based on the polarity and also on the molecular weight. And normally it's the polymer who plays on the surface of the particle, so we are getting better encapsulation efficiencies. In our group, in the CSIC, and also in collaboration with Bioinicia, we have encapsulated a lot of bioactives, probiotics, enzymes, polyunsaturated fatty acids, antioxidants, aroma compounds, vitamins, antibiotics, antimicrobials, a lot of compounds. And now I'm going to present fastly several case studies. We have encapsulated polyunsaturated fatty acids, the EPA and DHA, and those compounds are really interesting, really well known because of their health benefits. They are beneficial in cardiovascular diseases, anti-inflammatory fatty acids, anti-inflammatory diseases, also immune diseases and mental disorders. And those compounds are not synthesized in the human body, and we cannot obtain them from our diet, from the marine and fish oils. However, the intake is far below the recommended value, and consequently the need to implement those bioactive compounds in foods, pharmaceuticals, or supplements. However, their implementation supposes a technical challenge due to the loss of nutrients, toxic compounds, and bad smell and taste. We have encapsulated those omega-3 fatty acids in different materials, alcohol-based materials or water-based materials, and we have encapsulated in the particles obtained are in the micron range, around 1 micron or 2 microns, and the encapsulation efficiency was quite good, around the 85%. If we compare our particles with the commercial ones, we can see that our particles are in the very small, even for the scale-up process. We have followed the stability of those particles through FTIR, following the main functional groups, and we have observed that we can retard 2.5 times the degradation of the oil. As well, we have studied the stability to humidity and temperature, and we have observed that the capsules always provide a higher stability to the oil. As well, we have studied the storage stability at different conditions that we have called fridge, dryness, and ambient. And in the graphs, you can see that always the stability of the capsules is much higher than the stability of the free oil, being at ambient conditions, what we call ambient conditions, the conditions that provide the higher stability and really good conditions to the oil. We have studied the barrier properties of the encapsulating material through the permeation of the oxygen through the fluorescence decay method, and we have observed that whereas the encapsulated oil consumed 10% of the oxygen, almost the capsules did not consume like 2% of the oxygen. So the encapsulating material is a good barrier for the oxygen to avoid oxidation. And also, we have studied the barrier of the encapsulating material to aldehydes, which are the result products of the oxidation of the oil. And we have studied this through headspace gas chromatography, and we have seen that the same material could also retain those volatile compounds. Finally, with the omega-3, we have performed an organoleptic test, and our panelists have said that our capsules have little impact on the model product. In this case was reconstituted powder milk, even after 45 days of storage of the capsules. Well, now I want to show you the encapsulation of carotenoids and polyphenols. And those compounds also have a lot of health benefits. However, they present low solubility in water and are highly reactive and sensitive to temperature. And all of these affect to the bioavailability of those compounds. We have encapsulated beta-carotene in whey protein concentrate, obtaining spherical and spherical microparticles. And we have studied the UV stability of the free beta-carotene, which is the black line, and the capsules that are the gray line. And as you can see, where after 10 hours, the beta-carotene completely degrade, our capsules remained stable for a long period. Then we have encapsulated also resveratrol in gliadins, and we have obtained racing-like particles. This is common for the alcohol-based particles or alcohol-based encapsulating materials. And we have observed that the size of the particles in the range of the micron with a high encapsulation efficiency, and also the resveratrol maintains its antioxidant activity. We have observed that the particles were not soluble in water and they remain stable for a long period. And we have also studied the release of the particles in simulated gastric conditions. We have also encapsulated probiotics, and this supposes a challenge because we need that the probiotics arrive to the food product alive and metabolically active and abundant to be effective. So we have encapsulated Bifidobacterium animalis in pullulan and whey protein concentrate, obtaining microparticles. And studying the storage stability at different temperatures and at different humidities, we have observed that always the capsules provide a higher stability in comparison with the freeze-dried bacteria. Another approach that we have done for the encapsulation of the probiotics is to coat the probiotics with a layer of particles, in this case whey protein, maltodextrin, fibersol, that it's a kind of maltodextrin, and SANE. This was like a sandwich. And even in this case, we have observed that the particles, the sandwich, provide a higher stability than the freeze-dried non-coated bacteria. So by this technology, we can encapsulate omega-3 oils, beta-carotene and resveratrol, and also probiotics, and increase their stability. However, the disadvantage of this electrospraying technology for encapsulation is the low throughput. For this reason, we are involved now in another project that is called Capsule Tech. And the objective of this project is to increase this, to scale up, to increase the production to 10 tons per year. This is to reach or to provide the technology for the food industry scale. First of all, we have started developing the knowledge for the encapsulation with this technology that we call EAPG. And we have developed several formulations. The commercial of this study, the commercial results were 2 patents, several publications, and now we are developing our business model. We have selected as a model compound the omega-3 because this is really challenging, and to scale up the technology, we have performed a process optimization, taking into account the voltage, the different process parameters, the encapsulation formulation, and also the injector design. And we have characterized the particles in terms of microstructure, extractable oil, oil stability, and oxidation. We have performed two optimized systems with different particle size, one is smaller with medium particle size of 5 microns, and also another system with large particles that have a medium particle size of 15 microns. And both systems had really good results in terms of extractable oil, also moisture content, that its particles were dry, and the peroxide value, it's in the range of the recommended levels. And the yield of the process was really high, so in this scale system, we have reached the processing of the liter per hour. So we are now in the range of the food industry, whereas the conventional electrospraying technology produces or processes several milliliters per hour, and it's just good for the pharmaceutical industry. We have characterized the particles we have performed a stability test to UV light, and this test was characterized in terms of the peroxide value, and we have observed that the capsules have a really more stability than the free oil. And similar conclusions were obtained with the FTIR study. And also, when we study the permeation of the oxygen through the polymeric wall, we have observed that the oil consumed a lot of oxygen because it was oxidating, whereas the particles remain completely stable. So we managed to, with this process, to increase the scale of the technology, maintaining the quality of the particles in terms of morphology, encapsulation efficiency, and stability to the oxidation. And that's all. Thank you for your attention.
Thank you, Cristina and Maria. Thank you for your very nice presentations. I don't know if we have any questions. So I don't know if we have any questions for Maria and Cristina.
Can I ask a question?
Sure, sure.
I thank you very much for the very interesting presentation. I was wondering about something that you said at the beginning. So what is the real industrial exploitation of these two technologies at the moment?
We have in the company in Bioinicia, we commercialize the machine, so we can, one is our business model, and then we can also develop materials, or produce materials. So they are commercial level. So it's possible if there is an interest to produce fibers or capsules to achieve the market at the industrial scale.
Okay, thank you. And about, because in a European project we are working on bioplastics for food packaging, and at a very lab scale we are testing electrospinning for coating developments. Do you know anything about industrial application of these solutions, or production of coatings of plastics with electrospinning?
I think Maria can answer better this question.
Again, sorry?
About the scale of the Nano Pro and YPAC, if they are available at commercial scale.
I would say they are, at least at Bioinicia. We are actually the technology we talked about today, about this coating in the food packaging tubes. We are licensing this technology to a food packaging company, so it's definitely is closely to be commercialized, I think. So I think it has opportunities in this regard.
Yeah, I think so. Thank you.
Okay, so
I have also a question. Good morning to everyone, and thank you for the presentation. I was thinking if there is any study about the effects of these electrospinning technologies on some fruit proteins, about their structure, regarding, for example, immunoreactivity or allergenicity aspects. If there is any kind of fundamental study about how these technologies can have an impact on that topic.
We have not specifically looked into it, at least at Bioinicia, but I would believe there will be in the literature. What do you think, Cristina?
In terms of particles, since we are using all food grade materials, there is no concern about the safety of the materials. And I think it's always the same in the case of fibers, because we are using or trying to use biodegradable and materials. So we have not performed those tests, but in our case, I think this is not a main aspect.
No, especially since we worked mainly Cristina works mainly in the food area, but we at Bioinicia is more in the pharma stuff, which is even more strict. So we have not done the study itself, but we are very rigorous on this.
Okay, thank you very much.
Thank you. So do we have any other questions? So I have a couple.
Okay.
Hi, Cristina. Regarding the electrospray of omega-3 and fish oil, do you have any indication regarding the bioavailability of those compounds using the different techniques of electrospraying that you performed?
We have not yet measured. We want to perform the permeation test in CACO2 cells, but we have observed really good results in terms of stability, and we have also cut the particles and see that the droplets are really good distributed around the particles. So the oil is really it's well protected, and I think that we want to perform that test, but we have not arrived yet.
Okay, thank you. I would like to ask Maria regarding the superhydrophobic materials. What is the lifespan of the coating? So, for how long are they effective?
That's a very good question. We kept them, we stored them for up to 2 months, I think it was. And when we redid the water content angle measurements, it had lost it a little bit, but it was still super hydrophobic. So up to 2 months, we can say the coating was still there. And I think I can't say it shouldn't be gone even for longer periods of time. Of course, we have to test this, but I think the most problematic thing of this would be to try and scratch it off hardly, because with the thermal treatment, we managed to stick it there well, we stick it nicely, and even if you try to scratch it with a knife, it was sort of hard. But it would be more of an issue of people trying to push it very hard and removing it rather than the lifespan. If it's not damaged, it should stay there for long periods of time.
Okay, thank you. So I would like to thank you both for your presentations. If there isn't any other question, we will go on and move to Ricardo Pereira's presentation. I think you can share the screen, Ricardo.
I will share the screen with you.
Thank you.
Okay, I think you are now watching the presentation. So good morning to everyone. My name is Ricardo Pereira. I am assistant researcher at Center of Biological Engineering at the University of Minho. And with this presentation, I will briefly show you our competences in the FODIAC project. In particular, our expertise in this technology that I call electric field processing, but I'll try to explain you the main working principle and also applications of this technology. So I will start with a brief presentation of our center that is classified as excellent center and from the Foundation for Science of Portugal. And this center combines fundamental science with engineering sciences and covering several areas, namely biotechnology, engineering at food, environmental, health, and industrial levels. So we at the center, the number of researchers is almost 400. We have most of them PhD students, but also postdoctoral researchers that represent a large part of these numbers. About some numbers and facts, per year we published about more than 250 publications, most of them in Q1 journals. We have about 16 PhD theses per year, and about funding, external funding from projects, also a number of 5 million per year. And we also establish several spin-offs and patents along these several years. We also have a wide collaboration that led to development of joint researches and projects, academic programs also, and exchange of students and scientists. And regarding FODIAC project, this is our team. We bring expertise in the field of ammic heating treatment for bioactive extraction. Also some on emulsification technologies regarding stabilization viability, and also gut and in vitro models for the assessment of viability, namely by the dynamic studies of gastrointestinal digestion in vitro. And today I will particularly focusing on the ammic heating treatment. I will try to explain to you how it works. So ammic heating treatment you can find several names to this technology. Ammic heating is mainly the commercial name of the technology. It's not a novel technology, it's an emergent one. The first appearances were in 1920, and with the first study about pasteurization of milk. The technology by that time have some drawbacks because of the price of electricity and lack of technological components. But then after some time to grow up in about 2019, some studies appear again, and today the technology is established in an industrial way. We can find several companies that are producing equipment at an industrial scale. and also the scientific interest also raised during the last decade. So this technology can have the name of Joule effect, electroheating, moderate electric fields, and because of that, I think the best definition is electric field processing, because you can have some variations regarding application. And when we talk about ohmic heating, normally we talk about thermal processing, but we can apply electric field without applying a thermal component. So I think the best name for best definition is electric field processing, and I will, in the next slides, I will try to show you why. So how it works, mainly we have an electrical circuit, a simple electrical circuit with an energy source and with an electrical resistance, like a lamp. One is connected to power energy. So basically, how this can be applied in food processing. Mainly, we replace the electrical resistance by 2 electrodes that will contact the food product, and the food product will be placed between these 2 electrodes. So the food product will be, or the sample that we want to treat will be the electrical resistance of the circuit. When we supply with energy, the electrical current will pass through the food product. The food product will resist to that passage of the electrical current that will be dissipated into heat. So depending of the electrical characteristics of the material that we want to treat, this heat dissipation can be very high or very low. So we can have thermal processing or not, depending on that, and depending on the electrical conditions that we applied. Because of this, I like to call it electric field processing, because we have always one fact happening. We have always electric field passing through the food product. Heat is a secondary, it's an effect that can happen or not. So this technology is highly scalable. The same working principle can be applied at laboratory level, but also at pilot level. And this helps us very much to support fundamental research. Some of these equipments are available in our facilities. So what it's important to control on these treatments: electric field strength, that is related with the power level that you applied, the temperature that you want to work, the treatment time. Also some electrical parameters like electrical waveform, can be sinusoidal or quadratic, the electrical frequency, and also some effects that may happen depending on these parameters like electrolysis and chemical reactions. Regarding the product, it's important that the product have the ability to allow the passage of electrical current, and this is measured by electrical conductivity. Also the pH, the composition, and the microbiology will define the kind of treatment that you want to apply. So the main advantages of this technology, if you are talking about thermal processing, we can have a very direct and uniform and rapid way of heating, because we don't have hot surfaces, we don't have indirect, we don't have heat transfer mechanisms, because the heat is generated inside of the food product. So regarding food processing, this technology is highly suitable for viscous and particulate foods. We don't have temperature limit. We can go to the temperature that we want, because we don't have heat transfers limitations. It's considered a green technology or environmental friendly technology, because more than 98% of the energy is converted into heat, so we don't have heat losses, which is very important for industry. And we also have non-thermal effects because we have the passage of electrical current on the food product, and this can have some important effects regarding microbiology, regarding extraction or disruption of materials, and I will talk about that later. So main applications of this technology can go from nano to micro scale. So we can provide some electroporation on cell membranes depending on the electric field intensity that we apply. We can induce some molecular changes on some nutrients or some molecules like proteins. We can modulate enzymatic activity depending on the way that we apply electric field. But also we have some macrostructural changes regarding insulation behavior and tissue softening and disintegration. And we of course we have the thermal processing for pasteurization and sterilization that is the most widespread at the industrial level. So regarding our competencies in FODIAC project that are mainly related with extraction of bioactive compounds, I will try to show you some examples and case studies about this. So in this context, electric field processing shows great potential for extraction because electric field, when combined with heat, for example, we have a synergy and we can easily disrupt some biological structures, reduce use of water or any kind of solvents, and then trying to extract through an efficient and clean label approach. This is an example of extraction using grape seeds directly in the reactor. Another example was with extraction of phenolic compounds from purple potatoes, and in this case we also reduced use of solvents during the treatment. The potato pieces were placed directly into the reactor. We applied several strategies of treatment, such as instantaneous heating. We can go up to about 100 degrees in less than 1 second. Or we can also process the samples in a more with treatments that are not so aggressive, but take more time to perform. So depending on this, we can have different outcomes. This picture shows more or less what happens. Then we can, when we apply the treatment, we can have disruption of the structures, and we can have the leakage of some pigments and some important components. This is the pictures from extraction using purple potatoes. We also have another example is also the extraction using grape skins. Grape skins can be used directly as material to place in the equipment. They are natural ohmic conductors, so they conduct electricity very well. And depending also in the conditions of treatment temperature, we can have different levels regarding the extraction of anthocyanins, for example. And we also are working on study of extraction using microalgae biomass. And we have in our group research dedicated to the cultivation strategies that can help to produce these microorganisms and orientate the production for enrichment of biomass regarding protein content, lipids content, or for example, pigments content. So we can use the technology to extract some pigments or some proteins. This picture shows a sample without treatment and a sample with treatment, and we can be successful in extraction of chlorophyll, for example, when we apply this treatment, and then we can find several applications depending what you want to do. So novel perspectives about this technology. We are very interested on studying the effects that these electric fields may have on protein structure and interactions, because then we can develop nano or micro structures or control the development of these structures. We can also induce different gelation behaviors, and this is very linked with the way like proteins have their denaturation process during the treatment. And we are also looking for the impact that this can have on allogenicity, because this treatment is not identical to the conventional ones. So we should not assume that the same outcomes will have the same outcomes. So we started very recently a study about the effects that electric field processing may have on the immunoreactivity of beta-lactoglobulin, that it's protein from the whey fraction from milk that has a strong allogenicity component. So we are finding that depending on the conditions, we can modulate this kind of response. Depends on the electric field applied, but also on the electric frequency that we define in the treatment. So we find some conditions that you can reduce the immunological reactivity to the levels that are seen on the native protein, and this can be very interesting for future applications. So making a kind of sum up of this, and regarding the expertise that we bring to the project using this technology, conventional extraction using electric fields can be less time consuming and much more efficient, and we have also the advantage of being a clean technology. We can establish synergy effects by using fast internal heating. I say fast because it's a way of not degrading thermolabile compounds, because you can make a very fast heating without damage some important compounds. And we can combine this with the electric fields on extraction protocols for sensitive bioactive compounds. And there is a need of more fundamental knowledge about the interaction that electric fields have on some bioactive molecules and the interaction of these molecules with the matrices, and also the impact that destruction routes may have on the bioaccessibility of these molecules. This can be done only with a holistic approach, combining different competences by joining chemical, biological, engineering, and also biophysics. So I would like to thank for your attention, and if you have any questions, feel free to ask. Thank you very much.
Thank you, Ricardo. So if we have any questions for Ricardo, please fire away. So I have a question. First of all, thank you, Ricardo, for your very insightful presentation. I have a question regarding the extraction of compounds using the ohmic heating technology. Mm-hmm. So have you been able to, or are you planning to apply some sort of vacuum technology for the device? And I'm saying this because it will probably be helpful on the oxidation of bioactives, or also some overheating problems that might occur. I don't know if you have thought of this.
You are remember me that a very time ago, some years ago, when I began my PhD. This was one of the topic, was a possible topic of investigation to try to combine vacuum technology with some treatments to improve extraction. It is an idea. We are not developing that, but can be very interesting. The main challenge will be the equipment and the development of the equipment for that application. But I think today it should not be so difficult because the components are technological components are being improved very fastly. So can be a very interesting approach. Yes.
Great, thank you. I remember reading something about it, and I thought it would be helpful regarding the bioactives and all compounds, and that's why.
Yeah, and there is some kind of electrical hydrodistillation already where they make some kind of that, but I think should be improved. But yeah, I think it's a very possible way of improving the potentialities of the equipment and the technology. Yes.
Thank you, Ricardo.
You're welcome.
So we can welcome Lorenzo.
Yeah, just a few last words. Well, first of all, sorry for because I arrived late, so I had another meeting that well I couldn't escape. But well, first of all, thank you very much for all of you for attending this meeting. As you know, the situation of the COVID is getting worse, so it's not foresee that in the next month we can return to implement the secondment. So this is something that we have to be aware about this. So the alternative is in this meantime to continue with this kind of seminars or other activities among us, or prepare, I don't know, ideas for Green Deal call or whatever. So that could be a good set of activities to fill this gap. So for that, if someone of you want to prepare a new seminar, please just to tell me, and we organize another seminar for the next month, or yes, for December or January eventually. Okay. So from my side this is everything that I would like to share with you. If you have some questions or some comments for today, so we can take advantage for discussing or for comment now. Okay, so see you in the next seminar. Probably that will be in December. So if some of you want to share and to present in this seminar, please just let me know, and we organize the seminar. Okay. Okay. See you next month.
See you.
See you. Bye.
Bye. Bye.
Bye. Bye. Bye.
Thank you very much.
Goodbye. Thank you very much.
Thank you. Bye.
Bye. Thank you.